Okay, this statistics problem, number 4 and number 5 are very similar. So I'm going to do problem number 4. You do problem number 5, then on your own. So this is all about the randomization distributions, which we cover in class on Tuesday and Wednesday of the second week. Daniel recently discovered a new route to school. He wondered if the travel times were different for the two routes. He decided to do an experiment. He randomly assigned 5 days to the old route and 5 days to the new route. The mean travel time for the old route was 1.16 seconds longer than the mean travel time for the new route. To determine if this difference is significantly significant, he performed 200 randomization trial runs and created this distribution. Okay, so we need to piece this out a little bit. I want to really imagine what happened here. Daniel started a new route to school. We're all fine with that. But he wondered about the travel times, right? So he did an experiment. He randomly assigned 5 days to the old route, 5 days to the new route. Okay, so we've got two treatments, right? New route versus old route. We've got maybe a significant number of trial runs, maybe not. 5 and 5, that's questionable, but okay. And then we've got randomly assigned, right? So he probably took 10 days and kind of sorted them into piles of which day was going to be which route. So when he went on this route, the old route, it says the mean travel time for the old route was a little bit longer, right? 1.16. When he went on this route, he collected data. Maybe the first day it took him like, I don't know, 2 minutes or like 10 minutes and 15 seconds. Maybe the next day it took him 11 minutes and 2 seconds, right? So he collected data 5 days in a row, and then he took an average. He found a mean for that old route. Then he did the same thing on that new route. Maybe one day it was like 9 minutes and 12 seconds. Maybe the next day it was 10 minutes and 5 seconds, right? And then he took an average for the new route, right? So then they both have averages. But what he really cares about is the difference between them. Which one was shorter? It turns out the new route was shorter, and it was shorter by 1.16 seconds, right? Or the old route was longer by 1.16 seconds, right? So that's really what he's done so far. But now he wants to know if it's statistically significant, right? So statistically significant is where you do that randomization distribution. So randomization distribution is where you take one side. So first you find and locate. Well, first off, you go through and you take all the data you already had, right? You had those 10 data points, and you shuffle them together as if it didn't matter how they happened. And then you distribute them into two piles, pretending one is the old route and one is the new route. That's a simulation. And then you find the new means of both, and you find the difference. So you pretend that you went through the process again, but you know that randomization caused the difference. So how did he create one run for this randomization trial? First step, he took the data from the experiment and shuffled it, right? He randomly divided it into two piles. One labeled new route, one labeled old route, right? Okay, the third step is he found the mean of each. So I'm going to use this for mean. Found the mean of each pile. And 4, he subtracted the means to find the difference, right? And that's one run. And then that's when he plotted that on here, right? So he plotted those differences. So we're trying to see if what happens randomly and what happened in real life, how those two things compare. Because we want the thing that happened in real life to be statistically significant. If it could have just happened by chance, it's not worth paying attention to. So we see, well, what happens when it's random? We know this data is random. We know these mean differences. Over and over and over again, we plotted. So he did this over and over and over again 200 times, right? So what does the bar labeled 15 at the top represent? So this 15, what does it represent? It represents, if you notice here, this bar right here is from 0.75 to 1. It represents the number of random trials where the mean difference, where the mean of the old route was 0.75 to 1 second longer. Okay? So 15 of the times that he ran that randomization trial, the old route was taking 0.75 to 1 second longer. So you need to write that down, what I just said in B. For C, what percent of the random data had a mean difference that was more extreme than Daniel's difference? So this is where we actually use that. So what percent had a mean difference that was more extreme? So first off, we have to put Daniel's difference there. So 1.16, this is 1 and this is 1.25. So 1.16 is going to be somewhere right around in here, right? So everything from here to here is more extreme from the mean, right? Here's the mean. Everything from here to here is more extreme. But also there's stuff on the other side that's more extreme. So we've got to like plot the other side of it, right? You plot the opposite. So everything from here to here is also more extreme. So all of these random trials were more extreme, just through randomly separating the piles. This many, all of these trials were more extreme than what Daniel had when he really did his experiment. So let's count up how many that is. We've got 1, 2 here, that's 3, 7, 12, 22, 30. And then here, this bar is cut. It should have 14 in it, but it's cut. So I'm gonna guess that there's maybe 10 on this side of that bar. So 30, 40. So I'm gonna say 40 trials on this side were more extreme. And then on this side, 2 plus 3 is 5, 9, 15, 18, 27. And then on this side over here, that should be 11, but I'm cutting that in part. So what did I say that was? Shoot, I lost count. 7, 11, 9, 18, plus 9 more is 27. 27 plus, let's see, instead of 11, I'm going to guess that's like another 8 maybe. So 35 on this side. Okay, so 40 on this side, 35 on this side, so 75 altogether. 75 trials were more extreme than Daniel's actual experiment. But what percent is that? That's 75 divided by 200, because that's how many trials there were. 75 out of 200 trials were more extreme, right? And you can divide. I'm actually just going to do it half of this over 100, right? So half of 75. So that's 3, 6, 15, 7, 37.5. So 37.5% of the random data was more extreme than Daniel's. That is definitely not significantly significant. No, it's not significantly significant because Daniel's data would need to be, and you finish the sentence, need to be more extreme than, it needed to be within 5%, right? To be statistically significant, only 5% of this data could be more extreme. Otherwise, it's not statistically significant. So you write the rest of that explanation down. But this tolerance needs to be 5% or less. 37.5 is definitely not statistically significant. It means that this very much likely happened by random, by chance, not by cause. Now you do problem number 5.